The next thing that we want to look at is the rate. So the rate can be determined through two different methods. There's the rule of 300s and the 10-second rule. So most of us know the rule of 300s. It's basically the box method. And the 10-second rule is counting the QRS complexes on an EKG strip and multiplying by 6. So let's first look at the rule of 300s. So the way the rule of 300s is determined is you basically count the number of big boxes and you do 300 divided by the number of big boxes. So if we look here, if we do 300 divided by one big box, you get a rate of 300. If you do 300 over two big boxes, you get 150. If you do 300 over three big boxes, you get 100, and so on and so on. So that's the way you can use the big box method to determine rate. The important thing here is if you have changes in your speed, like we mentioned in a prior video, then this box method doesn't apply. And also, if you have an irregular rate, this won't really help you. And that's where the 10-second rule might be a little bit more beneficial. So let's first look at an example. If we use the box method, I usually try to find a QRS complex that nicely lands on the edge of one of the big boxes. So if you look here at the bottom at lead 3, the first QRS complex is a little bit after one of the big boxes, but then the second QRS complex nicely peaks at the edge of a large big box. So if you count from here to the next QRS complex, you go one big box, two big box, three big box, almost four big boxes, and you do 300 over 4, you know that this heart rate is going to be 75. So that's how you can use the big box method. The other way of doing it is by counting the number of QRS complexes on a page, and this is actually helpful specifically for two reasons. One, for people with an abnormal rhythm that's not regular, or two, in people that have bradycardia. So if we look at this EKG here, and we look at the rhythm strip at the bottom, we see that these QRS complexes are very wide apart. So you can automatically know that you can just count the number of QRS complexes and multiply by 6, and that will give you the rate. So we count here, we have 1, 2, 3, 4, 5, 6, 7, 8 QRS complexes. 8 times 6 is 48, so this heart rate is 48 beats per minute. So we looked at name date, we looked at gain speed, rate, and the next thing that we look at is rhythm. So rhythm is a very big topic encompassing lots of different rhythms, many of which we'll touch on during the tachycardia videos. But here I want to focus on how to read a normal sinus rhythm. So for normal sinus rhythm, there's two criteria that have to be met. One, you need a P before every QRS complex. And two, you need positive P waves in 1 and 2. So first, when we try to determine if there's a P before every QRS complex, I usually look at the strips at the bottom, the rhythm strips at 2 or V5. And looking here, we see that there is a P before every QRS complex. So we meet that criteria. The next thing we want to look at is 1 and 2. Here we want to see if there's a positive P wave, because if there's a positive P wave, we know that the foci for depolarization of the atria is coming from the S8 node. If you have a negative P wave, you still know that it's coming from the atria, but it's probably coming from a different focus and not the S8 node, so it wouldn't be a normal sinus rhythm. Here we see that 1 and 2 have positive P waves, so you know that this is likely a normal sinus rhythm because there are P's before every QRS, and the P's are positive in 1 and 2. The next thing that we look at is axis. To understand axis, first we have to understand what a positive and negative QRS complex is. It's pretty self-explanatory, but it can kind of get confusing when you have bundle branch blocks. The easiest way to understand it is whatever is predominantly positive. So if the QRS is mainly above the baseline EKG line, then you know that it's going to be a positive deflection. If a majority of it is negative below it, then it's a predominantly negative deflection. If it's equal on both sides, we call that equiphasic. So to determine axis, there's two ways to determine it. You can either use the thumb method or the vector chart. Many of us learn the thumb method because it's faster, it's easier, and you can use it on the fly. So what is a thumb method? The thumb method is when you kind of represent two of the leads, specifically 1 and ABF, with your left and right thumb. So 1 is your left thumb, ABF is your right thumb. And your thumbs are going to be pointing in the direction of the QRS deflection. So if we look at this example here, 1 is a majority of it is positive, so your left thumb will be pointing up. AVF, on the other hand, is negative, so your right hand is pointing down. So if your left thumb is pointing up and your right thumb is pointing down, you have a left axis deviation. On the other hand, if let's say one is pointing down, so your left thumb is pointing down, and AVF is pointing up, so your right thumb is pointing up, this will be a right axis deviation because your right hand is pointing up. If both of them are positive, that's a normal axis. If both of your thumbs are pointing down, then it's indeterminate because the axis is very off. So that's the thumb method. So one of the other ways that you can determine a QRS complex and the axis with it is by using a vector chart. So many of us might remember this from class, and you do not at all have to have this memorized, because if you use the thumb method, you can determine the axis a majority of the time. However, if you do have this on hand, either on your clipboard or you have this memorized, you can kind of better determine what the axis of the EKG is. Many of us learned this vector chart by finding the isoelectric EKG lead and then looking at what's perpendicular to that to see what's positive and negative, and then that being used to determine what the deflection of the axis is. I think it's a lot easier if you have this chart on hand or you have it memorized to just look at the most positive EKG lead and then look at the ones next to it in relation to determine where the vector is. So looking at this example again, if we look at what the most positive limb lead is from 1, 2, 3, AVR, AVL, AVF, then we see that AVL is probably the most positive, right? A1 is also positive, but is not as positive. So looking at this, looking at the chart, we know that the vector is going to be in the AVL direction, and it's going to be more towards AVL than it is towards 1 because AVL is more positive. Also, if we look at 3, which is the most negative, we know that this vector is going to be completely opposite to 3. So therefore, the vector is going to be in this area here in AVL, so it will be a left axis deviation. Again, if you use a thumb method, you'd find this the same way, and this is definitely taking more steps. However, this is another way of determining the axis.